Thanks, Dale. Can you hear me okay?
Yep.
I can just talk in this, okay, this conversational tone. Excellent. So I'm one of those people that Darren referred to in his introduction to the conference as not a biomass utilization expert. And when I was contacted about this, I was like, why me? And he talked me into it somehow. But I'm not going to talk about biomass utilization as such, as we've heard in the talks from this morning, which I've learned I've tripled my knowledge about biomass utilization so far in this conference. But I'm going to talk instead about landscape restoration treatments in the Great Basin, which is the piece of real estate that I know best. So I'm going to talk about landscape restoration treatments that provide an opportunity for biomass utilization. Let's see if I can figure this out. Okay. So first, I'll provide some historical context on woodland dynamics with reference to the Great Basin Pinyon Juniper woodlands. Then I'm going to remind ourselves about what ecological restoration is, because I should probably say what the title of my talk is. Can biomass use of Great Basin Pinyon Juniper woodlands be considered ecological restoration? So from the title of this conference, I gather that most of us have moved beyond that question, and that the answer is a resounding yes, but being the contrarian that I am, I want to revisit it and provide some analysis to that question. So first, historical context. Second, remind ourselves what is ecological restoration. Third, I want to introduce a woodland classification that's vegetation dynamics based that I'm hopeful would inform landscape level ecological restoration. And fifth, I want to finish with some conclusions. So first, for context of the woodlands, I want to start with the deep history, such as one might infer from pack rat middens or from paleoecological studies using pollen analysis. So what we know from studies by Bob and Cheryl Nowak and Robin Tausch and several others is that over the last 30,000 years, the Utah juniper species range has been fairly stable with relatively minor elevational shifts in association with climate change, while the single-leaf pinyon has been incredibly dynamic. It's fluctuated greatly, and not only that, but it's relatively new in the Great Basin region. So it's arrived in the Nevada part of the Great Basin just over the past 3,000 years, and this northward expansion is still ongoing. So there's the arrows showing the past 3,000 years progression. The species doesn't occur much above the Humboldt River in eastern Oregon or the Truckee River, eastern Nevada, or the Truckee River in western Nevada. There's a population, one of the northernmost populations in Utah. Steve Gray and Julio Betancourt and others have dated that initial establishment to the year 1246, and that's the Dutch John Mountain in the Uintas. So it might even not be shown on my map. So the single-leaf pinyon is a relative newcomer to this region, and it's still expanding its range. So that's the deep history, now quickly moving from multiple millennia to multiple centuries. And to reconstruct the dynamics of the pinyon juniper woodland over multiple centuries, we rely often on tree ring studies that use tree rings to date the ages of individual trees, or in some cases find fire scars and date past fire events and reconstruct past fire frequency and fire severity and fire size from this tree ring data. So this shows my former graduate student, John Bauer, taking a slab out of a pinyon tree. Actually, it's a wedge. We left the tree standing. This one only had one fire scar, and we dated that fire to the year 1800 as part of a fire chronology used to describe historical fire regimes. So I'm going to focus on two fire history studies. One is the study that John Bauer and I did that was published in 2009 in central Nevada in the Shoshone Mountains. And another study recently published from Franco Biondi and others also at my institution at UNR. And his study was in southeastern Nevada in Mount Irish. It would be right around there in a mixed ponderosa pine, single-leaf pinyon pine woodland. We don't just want to describe the natural fire regime, but we want to quantify how the natural fire regime has changed over time and what the causes are of that change and what the implications of that are for the current changes in pinyon juniper woodlands that we're seeing. So to summarize 3 years of my graduate students' work in just one slide, which is why this is so busy, for the Central Nevada study area, we found a long fire rotation of over 400 years. The fire rotation is the number of years that it takes to burn an area the size of the study area. So fires were fairly infrequent in the sense of fire rotation, yet there were a lot of small fires. So fires were frequent in the one, if you look at it one way, but infrequent if you look at it on an aerial basis of how long it took to burn a fairly large area. So there were 44 unique fire years. The fires were reconstructed as being all of high severity. And fires were fairly frequent in the mid-1800s, kind of peaked in the 1870s, associated perhaps with early mining activities, or maybe that had nothing to do with it. And then, well, there hardly have been any in this particular study area, which we think in some ways is representative of these central Nevada mountainous areas, in other ways less so. So that's what we found. Then looking at Franco Biondi's study in Mount Irish. So here I flipped around the x-axis on you, which in the previous slide, time is going from right to left, and the number of trees recording a fire are on the y-axis there. In this case, we have time going from left to right, and the number of fires recorded in each year is the y-axis here. So ignore these lines and pay attention to the vertical bars, and you see that they found much the same thing. They had a peak of fire in the late 1830s, and then very little fire in this study area, which is a mixed ponderosa pine pinyon woodland since the mid-1800s. However, in their case, some modeling work that they did suggests that that absence of fire since the mid-19th century is associated with climate variability, as opposed to other settlement era influences like maybe overgrazing that would have reduced fine fuels or a reduction in Native American fires. So similar overall results from the two studies. So what do we get out of this absence of fires in the last century and a half or so? At the same time period, that's associated with dramatic changes in our Great Basin landscapes, where we have conifers expanding into the sagebrush valleys, into the canyon bottoms, also going upslope into the productive shrublands, higher into the mountains. And generally, the woodlands are becoming denser, and we're seeing an increase in tree dominance and tree density. The effects of increased tree density, well, as trees dominate the stand, you tend to lose the understory. So this is showing that stage of stand development where trees are competing intensively with each other, so there's greater mortality of overstory trees. And also, we have a lot of sagebrush skeletons in the understory that soon will become flatter and a little harder to see as time progresses. So obviously, it's a situation of very heavy and continuous fuel loads at this time of stand succession. And we've heard earlier this morning about the large stand replacing fires that we've had throughout the West. So this is Wall Canyon and the Toyabe Range in central Nevada, a very large, pretty much stand replacing fire with some aspen resprouting in some of the upper watersheds. But the pinyon juniper woodland is pretty much gone. And the cheatgrass invasion has been heavy. So after these stand replacing fires, we tend to get cheatgrass dominance and a cycle of the highly flammable cheatgrass burning in subsequent years, and we get what's referred to as the grass fire cycle. But you're all very familiar with this sad tale here, and I don't think I'm telling you something new, not this audience anyway, and this isn't what most of my talk is about. I'm building up, giving some background. So more historical context. I've talked a bit about the natural range of variability, recent ecological change. Now, since it's a conference in biomass, I want to talk about historical biomass manipulations and perhaps some of the consequences of that. So biomass use has happened before in this part of the country since settlement. The charcoal was used to process ore during the early days of mining before the mercury amalgamation process was invented to extract the gold from the ore. And a great amount of wood charcoal must have been required to sustain this industry. So in a few locations, we still have these beehive kilns, as they're called on account of their shape, that the Italians, maybe we're not all Italians, but you read about it that the Italian stone masons were brought in to build these, but I'm sure other ethnicities were probably involved. I'm trying to be politically correct, I guess. But one of these kilns, these are about 100 cord kilns in terms of their capacity, would have required 3 to 4 weeks to burn. And if you assume 20 to 40 hectares of woodland, depending on tree density, to get those 100 cords, the math works out that one kiln burned 1 hectare or 2.5 acres per day. So maintenance of these kilns, if they had been in continuous operation, would have required massive acreages of woodland. And even if I'm overestimating somewhat, still the presence of these kilns on the landscape means that a large acreages of trees, of tree-dominated areas would have been utilized for this early mining industry. Now, we don't see these charcoal kilns in a lot of places, and that's because most of the charcoal operations were too small and too temporary to make it worthwhile to construct those large beehive-shaped kilns, which must have been quite an effort in terms of manpower and time. So more commonly, they dug pits in the ground, and they used some wooden construction, and then to elevate the pits, and then they stacked them up full of fuel wood, and they just lived on site and monitored it while the wood burned to charcoal. So there are these charcoal pits that were more commonly constructed, which, if you go out with some archaeologists who specialize in this, they can tell you what they look like. And, well, they look like this. This is one in the Pine Nut Mountains of Nevada. And this is a close-up of the ground in the middle of that somewhat bare patch. And it's all charcoal, and you could stick your hand in it up to about the wrist. But just driving around, and until I went out with the archaeologists, I think I passed a lot of those and not known them for what they were. And then down the road, another 200 meters, maybe half a kilometer, there's another one of those. And then there's another one, and they're like 6 in a row along the dirt road, which corresponds to the old wagon roads that they would have used to haul the charcoal back out to the processing site where they would have processed the ore. So the wood would have come from the hill slopes to these charcoal pits in the valley bottoms where the roads were. They would have processed it into charcoal and then transported the charcoal, which is much lighter than wood, to haul in the mule trains. And then when the trains came, when the railroad lines came down to this region, they would have loaded it up onto the trains. So they're detectable today, but difficult to recognize. For an interesting modeling study, my postdoc Dongwook Ko and I developed a spatial modeling approach to predict the impacts of this charcoal logging, because we'd heard estimates like the whole area within a 50-mile radius of Eureka was basically a moonscape because of the charcoal logging, and that didn't seem very scientific or very reasonable to us. So it seemed like a process of resource utilization that was modelable. So we used a model that's commonly used to model the grazing effects of cattle as associated with watering holes, to model the harvesting effects of people as associated with these mills, basically, where the charcoal would have had to have been transported for operation. And we incorporated in our model how the different processing levels of the different mills changed over time. So we used historical data on production, and we used historical data on the development of the lateral railroad lines, the Palisade-Eureka Railroad, the Nevada Central Railroad, off the CP, the Central Pacific Railroad line. So there you can see there's Battle Mountain. Reese River corresponds to about where Austin, Nevada is today, Eureka, Nevada, for this fairly large area in central Nevada. We validated our model using data that we found on old axe cut and old saw cut stumps and just old logging camps where we could find evidence of that. So we tried to develop the best predictive model that we could of these impacts. as it unfolds over time, so 1878 to 1880 to 1895, by shortly after 1895, they were done doing this, basically. They were no longer using charcoal for the mining industry. They were using chemical methods involving arsenic and cyanide. So these were fairly short-lived impacts over a couple of decades in this landscape. So, and our model included slope steepness. We had an energy cost model in there. And this is what it looked like in 1895, extracting just the areas of Pinyon Juniper woodland. So the darker red colors are places that would have had greater impacts of charcoal logging. The green colors and the yellow colors would have had much lesser impacts. So what we've done is, instead of saying that within a 50-acre radius circle of Eureka there were big impacts, we've tried to model it just so we can use that information to better understand recent dynamics of woodlands on these landscapes. We were going to validate it for this big area, but we ended up using just this small area for validation and had a pretty good relationship. Our area under curve statistic was greater than 0.7. I'm trying not to show data in this talk, but the paper is available if you want to look into the details. So I'll talk a little bit more about what I think this means later on. To some of you, it might just be an interesting footnote in history that means nothing. And to others, it might be an important piece of historical context. Another piece of historical context, 100 years later than that, several decades ago and continuing to fairly recently, there's been chaining as a management practice in Pinyon Juniper landscapes, or the dragging of anchor chains behind bulldozers as a management response to woodland expansion to reestablish pasture for livestock and habitat for wildlife. So from 1960 to 1972, maybe over 1/3 of a million acres were chained. I don't know the exact number, or if there's even a very good estimate of it. But it generally wasn't that successful in that it didn't establish good forage for the most part, and the trees came back quickly. So it didn't really establish its management objectives. And since the trees came back quickly, mainly from knocked over saplings, so you can see here, these are photos from shortly after the chaining. These are photos from just 3 years ago, same locations. These are photo pairs taken by Robin Tausch, who's in the audience, who took both before and after photos. But you can see that there are knocked over tree saplings and advanced regeneration after the chaining. And you can almost see the same saplings growing up into trees in this photo if you look carefully. It was supposed to knock trees back for a longer period of time and establish an understory with forage values, and also an understory that could keep cheatgrass out from invading the site and would keep surface soil in and would have benefits for hydrology. There's many benefits that were supposed to happen that probably happened in some of the chainings, but by and large, I'll talk a little more about it. So you end up with an ungainly sort of post-chaining woodland because it's this advanced regeneration of these leaned over saplings. And with Robin Tausch and my master's student Nathan Bristow, we did a study comparing long-term recovery of the chaining sites with long-term recovery of a cluster of prescribed fire of burn sites that were in the White Pine Mountains. The chaining sites were in the Kern Mountains and several other locations in eastern Nevada. So this photo shows a site from the South Kern Mountains, chaining, and a burn site. The chaining and the fire happened at about the same time. And you can see that one met restoration goals and the other one didn't. And it's kind of clear which is which. So we have a master's thesis and hopefully papers coming out soon with the details and the graphs that I'm not showing for herbaceous understory species, shrubs, and trees that came back associated with these sites. So since I only have 10 minutes left, I'm going to accelerate. Let's remind ourselves what ecological restoration is. Back to the title of my talk. So This is the definition. So there's many definitions of ecological restoration. One of the problems with the word is that it means different things to different people. But looking at the Society for Ecological Restoration International definition, it's the process of assisting the recovery of an ecosystem that's been degraded, damaged, or destroyed, which begs the question, what do they mean by recovery? So they go into that then. An ecosystem's recovered and hence is restored when it can continue its development without further assistance or subsidy. In other words, it's self-sustaining and it demonstrates resilience to subsequent disturbance. So if disturbance happens, that kind of ecosystem or vegetation type or plant community will maintain itself. So self-sustaining and resilient. So back to the question of whether removal of pinyon pine and juniper constitutes ecological restoration. It's self-sustaining if it won't go back to trees normally through successional processes. It's resilient to disturbance if it won't become invaded or dominated by exotic plant species following fire. So that generally requires that the removal of the trees is also associated with the establishment of a vigorous native perennial understory that can resprout or reseed following fire and outcompete cheatgrass. It's recovery if it's not conversion of a persistent woodland to some different vegetation type. I'll get into what persistent woodland means later. So really we need to rephrase the question not to is removal ecological restoration, but to under what conditions is removal of pinyon pine and juniper trees ecological restoration. And this requires a classification of woodland condition. So I'm going to present a woodland classification, or actually I'm going to review a few woodland classifications and then present my own in the hopes that such a classification could help to inform landscape level restoration. So this is a classification of tree dominance in expansion woodlands that many of us are familiar with, that Robin Tausch came up with or was instrumental in developing. That's based on the amount of leaf biomass in the understory relative to the amount of leaf biomass of the overstory trees over successional time on the x-axis. Phase 1 woodlands are dominated by understory biomass. Phase 3 woodlands are dominated by tree biomass. And in the middle, there's a rapid transition. There's a threshold effect when things change very quickly and trees quickly begin to dominate from understory species. A problem with this classification for landscape restoration, or I shouldn't say a problem, but a limitation, is that it's only for expansion woodlands and doesn't help to inform the question of what are expansion woodlands versus what are persistent woodlands. A more biogeographical classification, which isn't very dynamic though, from a paper by Bill Rami and others, published in 2009, deals with the relationship between climate and vegetation type. So that if you have sufficient moisture for trees, you have a tree-dominated system, and it's a persistent woodland. If there's less moisture so that tree establishment is limited, but if precipitation comes in the summertime so that you have more shallow, short-lived moisture supplies, then you have a savanna, a grassy system with scattered trees. If, on the other hand, you have winter-dominated precipitation, so precipitation's from snowpack that melts and then you have deep moisture that's stored for a longer period of time and where trees can access it, which is what we have in most of western and central Nevada, then it's a wooded shrubland. Wooded shrublands are described in Rami et al. As being dynamic areas of change between low and high tree dominance associated with climate and disturbance. Sounds familiar to me as somebody who studied the Nevada pinyon juniper woodlands. And generally in our region, as we go east or south, we get into more of the summer-dominated precipitation. It's more of a monsoonal climate. And west and north, it's more winter-dominated. Another 5 minutes. Another classification is more focused on the disturbance history. And this is an example, again, from that Bauer and Weisberg paper that my student took the lead on. You can classify woodland as being old-growth woodland in places that have old trees, or maybe a mixed age class, and no evidence of previous fire. Fire just hasn't been an important part of that type of woodland. You can classify woodland as establishing after a stand replacing fire, or a mixed severity fire, or a low severity fire. Or then there's expansion woodland, which is where trees have established in another community type with no evidence of prior disturbance. In this particular study area in the Shoshone Mountains, most of the stands established after high severity fire, whether they were old or young. 5 out of 84 were expansion woodlands, and about 9 were old growth woodlands with no evidence of fire at any time in the past that could be reconstructed. So a figure, a reconstructed fire polygon shows stand origin dates. The oldest trees dated from 1887, 1884. A number of fire scars just in one area from 1865. We dated the fire polygon then to 1865, surrounded by old woodland from the 1500s. So this is a post-high severity fire woodland that could be confounded with an expansion stand today if you didn't have this disturbance regime context, because all of the trees date from the late 1800s or later. And without doing the fire history study, you would not know that. If you look at this area here, we don't really know if the fire extended that far. We don't have good enough data to resolve the exact boundary of a past fire. That's what it looks like today. Is this expansion woodland or post-fire woodland that's taken a very long time to succeed back to a mountain shrub community and then to have tree establishment in it? We don't know the answer to that. So a classification based on vegetation dynamics can divide the world into persistent woodland or expansion woodland, wooded shrubland. It's kind of a simplification, but let me break it down a little bit more. So persistent woodland can be what many have referred to as old growth woodland, which has some old trees in it, and no evidence that it's established following fire. You can also have persistent woodland, which might not have old trees, but might be a post-fire woodland. And you can have persistent woodland that might be post-deforestation event, and also not have old trees. So the types B and C are often mistaken for expansion woodland. How to tell persistent woodland from expansion woodland? We can look for old trees. That works for type A. And I don't have time to, I'm going to skip through this one, but I published a paper recently with a postdoc that provides guidelines for how to tell whether a tree is old or not without coring it and aging it. And I could provide that information, or somebody can just ask me about it later on. But absence of old trees is not a sufficient indicator of expansion woodlands. So you also need to look for the fire evidence and look for evidence of extensive harvest, not just on the site, but in the vicinity. So are there charred snags and logs? Are there fire scars? Are there fire-associated exotic invasives or early seral plants, which might be a clue that a fire happened there at some point? And is there evidence of extensive harvest, axe cuts, cross-saw cuts, charcoal pits and platforms, which might not be as obvious to find as you'd think. Expansion woodlands can be of at least 2 kinds. Tree invasion caused by overgrazing and fire exclusion. We had that long period of absence of fire since the late 1800s, and in many parts of the landscape, trees have used that as an opportunity to invade. Or there can be expansion of tree species range in response to favorable climate conditions, both altitudinally, latitudinally, shifting across one slope aspect to another, north slopes to south slopes. And telling these apart is something that I'm trying to work on. It's actually a very difficult problem. So appropriate restoration goals by woodland type. So if it's a persistent woodland, you can argue for no action. If risk of high severity fire is a concern, you could argue for thinning or fuel breaks or things that reduce the risk of high severity fire. If forest health is a concern, you could argue for thinning and pruning activities that reduce susceptibility to drought, mortality, and pathogens. And he's about to, okay. In the case of tree invasion, that's where it makes sense to convert from a forested to a non-forested vegetation type, perhaps. But there it's very important to establish perennial herbaceous understory vegetation so that you have the resilience component, so that following disturbance, that stand won't be invaded by cheatgrass or exotic weeds. And if it's expansion of tree species range in response to climate, maybe it makes sense not to do anything unless it's trumped by the other concerns. Since I'm out of time, I'm just going to leave my concluding arguments up there for you to read while you think about questions to ask me.
Thank you, Peter.